Procedural application for distance calculation. Welcome, everyone. In our previous lessons, we spent a significant amount of time establishing the theoretical formulas required to find the shortest distance between various types of lines in three-dimensional space. You now have the mathematical tools in your toolkit. However, I know that when you sit down to solve a complex problem, the real challenge isn't just knowing the formulas. It's determining which specific formula to apply to a given pair of lines and executing those multi-step calculations without making a single computational error. That is why today's tutorial is designed differently. Instead of just looking at formulas, I am going to provide you with a structured, step-by-step pedagogical approach. My goal is to teach you how to approach these problems systematically, so you can move from reading a problem to finding the correct solution with confidence and precision. Step-by-step procedure. Now that we have established the theoretical formulas in our introduction, let's look at how we actually put them into practice. To find the shortest distance between two lines without getting lost in the complexity, you should follow these 5 logical steps. Step 1. Identify the line type. Now that we've established that we need a structured approach to solve these distance problems, let's dive into our very first step. Before you even touch a formula, you must first determine the geometric relationship between the two lines you are working with. Think of this as the diagnostic phase. To do this, you'll look closely at the direction vectors, which we call B1 and B2. First, check if the lines are parallel. You can tell they are parallel if the first direction vector, B1, is simply a scalar multiple of the second direction vector, B2. In other words, if you can find some constant, let's call it k, such that B1 equals k times B2, then you are dealing with parallel lines. On the other hand, if these direction vectors are not scalar multiples, meaning you can't find that constant k, then the lines are either skew or intersecting. Now, a quick tip for your future calculations. To distinguish between these two, you would typically check if the shortest distance ends up being 0. If your final calculation results in a non-zero distance, then you know for certain the lines are skew. This identification is crucial, because as we will see in the next few slides, the formula you choose in step 4 depends entirely on which of these relationships you've identified here. Step 2. Extract components. Now that we have completed step 1 and determined the geometric relationship between our lines, we move on to step 2, which is the extraction phase. Once the lines are identified, your next task is to carefully extract the necessary vector components from the given equations. First, you need to identify the position vectors. These are represented as a 1 with a vector arrow over it, which is a point on line 1, and a 2 with a vector arrow over it, representing a point on line 2. Think of these as your starting coordinates on each line. Next, you must identify the direction vectors. We denote these as B1 with a vector arrow over it, representing the direction of line 1, and B2 with a vector arrow over it, for the direction of line 2. These tell us which way the lines are heading in three-dimensional space. Just a quick note here to keep in mind for your calculations. If you determined in the previous step that the lines are parallel, you actually only need one direction vector, which we will call B with a vector arrow over it. This is because, in parallel lines, the two direction vectors are collinear, meaning they point along the same path. Once you have these components extracted, we will be ready to move to step 3 and calculate the vector difference. Step 3. Compute vector differences. Now that we have successfully extracted our position vectors and direction vectors in the previous step, we move on to step 3. In this stage, we need to calculate the vector that physically connects the two known points on our lines. We can refer to this as the vector st. To find this, you simply perform a vector subtraction. Vector a 2 minus vector a 1. Think of this vector as the displacement, or the straight line bridge, between the starting points of our two lines. It is a vital piece of the puzzle because this specific vector is a critical component used in both the formula for skew lines and the formula for parallel lines that we will apply in the next step. Step 4. Apply the appropriate formula. Now that we have identified our line types and extracted all our necessary components in the previous steps, we reach Step 4. This is the most critical part of the process, selecting the correct mathematical tool based on the identification we made back in Step 1. First, let's look at the case for skew lines. If you determine that the direction vectors are not scalar multiples, you will use the formula representing the projection of our connecting vector onto the common perpendicular. In words, the distance, d, is equal to the absolute value of the cross product of b sub 1 and b sub a 2, dotted with the vector a sub 2 minus a sub 1, all divided by the magnitude of the cross product of b sub 1 and b sub a 2. On the other hand, if you identified the lines as parallel, you must use a different approach involving the cross product of the direction vector and our connecting vector. For this case, the distance, d, is equal to the absolute value of the cross product of b and the vector a sub 2 minus a sub 1, all divided by the magnitude of b. Keep these two formulas distinct in your mind, as choosing the wrong one will lead to significant errors in your final calculation. In the next slide, we will walk through the specific order of operations you should follow to simplify these complex expressions. Step 5. Simplify and calculate. Now that we have identified our lines and extracted all our necessary components, we need to talk about the actual execution. Slide 7 is perhaps the most important for avoiding calculation errors, as it outlines the specific order of operations you should follow. Think of this as your mathematical checklist. First, you must perform the cross product. Depending on what you found in Step 1, you will either calculate the cross product of b1 and b2, or, if the lines are parallel, the cross product of b and the vector difference of a 2 minus a 1. This step is crucial because it establishes the direction of the common perpendicular. Second, if you are dealing with skew lines, you will then calculate the dot product. You'll take the vector you just found from the cross product and dot it with the vector difference of a 2 minus a 1. This step essentially projects our connecting vector onto that perpendicular path. Third, you need to find the magnitude, or the length, of the resulting vectors. Specifically, you'll be looking for the magnitude of the vector produced by that cross product. Finally, the last step is simple arithmetic. Divide the value you got from your dot product by the magnitude you just calculated. This will give you the final scalar distance. If you follow this sequence, cross product, then dot product, then magnitude, and finally division, you will maintain a clear logical flow. We are about to see this exact sequence put into practice in the next slide with a real-world example involving communication cables. Illustrative example. Now that we have walked through the theoretical framework and the 5-step procedure, let's put everything we've learned into practice with an illustrative example. Imagine a real-world scenario. You are an engineer inspecting 2 communication cables running through a building. To ensure there is no interference, you need to find the shortest distance between them. The path of cable 1 is given by the vector equation r equals I plus 2j plus 3k. All plus lambda times the quantity I minus j plus k. The path of cable 2 is represented by the vector equation r equals 2i minus 3j plus 4k. All plus mu times the quantity 2i plus 3j plus 6. Our objective is to apply the systematic steps we just discussed to calculate the exact shortest distance between these 2 cables. Let's move on to the next slide to begin our step-by-step solution. Step-by-step solution. Now that we have our scenario, let's walk through the solution step-by-step, applying the procedure we just discussed. First, we begin with Step 1, identifying the line type. We need to look closely at our direction vectors. Here, vector b, 1 is I minus j plus k, and vector b, 2 is 2i plus 3j plus 6k. To see if they are parallel, we check if one is a scalar multiple of the other. If we look at the ratios of the components, 1 divided by 2 does not equal negative 1 divided by 3, and neither does that equal 1 divided by 6. Because these ratios are inconsistent, there is no constant k that works. This tells us the lines are not parallel, they are either skew or intersecting. Moving on to step 2, we need to extract our components from the original equations. We'll pull out our position vectors and our direction vectors. For the first line, vector A1 is I plus 2j plus 3k, and its direction, vector B1, is I minus j plus k. For the second line, vector A2 is 2i minus 3j plus 4k, and its direction, vector B2, is 2i plus 3j plus 6k. Having these clearly listed is vital for the next steps. Finally, for step 3, we compute the vector difference. We need to find the vector connecting our 2 points, which is vector A2 minus vector A1. We subtract the components of the first vector from the second, 2 minus 1 for the I component, negative 3 minus 2 for the j component, and 4 minus 3 for the k component. This leaves us with a resulting displacement vector of I minus 5j plus k. We'll use this specific vector in the very next step to apply our formula. Step-by-step solution, continued. Now that we have identified our lines as skew and calculated our connecting vector, let's move into step 4, where we actually apply the formula for skew lines. First, we need to find the cross product of our two direction vectors, b1 cross b2. To do this, we set up our determinant using the unit vectors I, j, and k, followed by the components of our first direction vector, 1, negative 1, and 1, and then the components of our second direction vector, 2, 3, and 6. Calculating this out, for the I component, we take negative 6 minus 3, which gives us negative 9i. For the j component, we take 6 minus 2, which gives us 4, but remember to apply the negative sign from the determinant formula, leaving us with negative 4j finally. For the k component, we have 3 plus 2, which gives us 5k, so our resulting cross product vector is negative 9i minus 4j plus 5k. Next, we need to find the dot product of this new cross product vector and the vector difference we calculated in the previous step, which was a 2 minus a 1. We take the components of our cross product and multiply them by the corresponding components of our difference vector, negative 9 times 1, negative 4 times negative 5, and 5 times 1. When we sum these up, we get negative 9 plus 20 plus 5, which simplifies to 16. We'll use this value of 16 in our final step to find the actual distance. Step-by-step solution, continued. Now that we have successfully calculated the dot product in the previous step, we move into our final stage, step 5, which is to simplify our results to find the actual distance. First, we need to find the magnitude, or the length of the vector we found from our cross product. Looking at our previous calculation, we have the vector negative 9i minus 4j plus 5k. To find its magnitude, we take the square root of the sum of the squares of its components. That is, the square root of negative 9 squared plus negative 4 squared plus 5 squared. When we square these, we get 81 plus 16 plus 25, which simplifies to the square root of 122. Finally, we can plug everything back into our distance formula. We take the absolute value of the dot product we found earlier, which was 16, divided by the magnitude we just calculated, the square root of 122. When you perform that division, you get approximately 1.45 units. So, there you have it. The shortest distance between our two communication cables is approximately 1.45 units. In the next slide, I will highlight some common pitfalls to watch out for so you can ensure your calculations remain accurate in future problems. Common mistakes to avoid. Now that we have worked through our illustrative example, I want to pause and discuss some common pitfalls. Even when you understand the theory, these specific errors can easily lead to incorrect answers during an exam. First, let's talk about incorrect formula selection. A very frequent mistake is attempting to use the skew line formula when the lines are actually parallel. If you try this, you'll find that the cross product of the direction vectors, b sub 1 cross b sub 2, equals 0. This leads to a mathematical impossibility, division by 0. So always perform that initial check for parallelism as we discussed in step 1. Second, watch out for sign errors during vector subtraction. When you are calculating the difference between the position vectors, a minus a 1 it is incredibly easy to lose track of a negative sign, especially when the coordinates themselves are negative. I have also seen many students accidentally add the vectors, a 2 plus a 1, instead of subtracting them. Precision here is vital because this bridge vector is the foundation of your entire calculation. Third, do not forget the absolute value. Remember, we are calculating a distance, and distance is a scalar magnitude. It represents a physical length, which can never be a negative value. Always ensure you apply the absolute value bars to your final result to keep the magnitude positive. Finally, be careful not to confuse your components. Ensure you are not using the direction vector, b, in place of the position vector, when calculating your vector difference. Mixing up these two roles will completely change the geometry of your problem. Keep these points in mind as we wrap up our session with the final key takeaways. Key takeaways. First, always start with your parallelism check. Remember, you must examine your direction vectors. If vector b1 is equal to a constant k multiplied by vector b2, then you can conclude that the lines are parallel. On the other hand, if vector b1 is not equal to a constant k multiplied by vector b2, then you are dealing with lines that are either skew or intersecting. As we saw in our example, this is the signal that you'll likely need the more complex skew line formula. Next, keep in mind the concept of the bridge vector. The vector calculated by subtracting position vector, a 1 from position \vec2$, is the essential link between the two lines. This displacement vector is a critical component in every calculation we've performed today. Finally, to avoid calculation errors, stick to this specific order of operations. First, compute your cross product. Second, find the dot product. Third, determine the magnitude of your resulting vector. And lastly, perform the final division to find your distance. All right, we have reached the end of our tutorial. Before you move on to your practice problems, let's quickly recap the key takeaways from today's lesson to ensure you have a solid foundation. If you follow this systematic approach, you'll be able to tackle even the most complex three-dimensional geometry problems with confidence. Great job today!